Can you hear me on the screen?
Sir, you just present your PPT, sir.
Okay.
Just to present your PPT, sir.
Yeah, 1 minute.
Sir, headphones, sir.
Sir, one direct, sir, கொஞ்சம் வாங்க sir.
Can you see the PPT?
Sir, no, sir. You just present, no, sir. Present your screen, sir.
I did that thing. Just wait.
Yeah. Open your PDF, sir, first.
What do you want me to do?
First,
I open my PPT. So
then come to Google Meet, sir.
Oh, that's what I did. I am on Google Meet right now.
Okay. Just click on the button present now screen, sir. In the right top, right bottom corner, sir.
Right bottom. Which one?
Present now.
Present. Yeah, present now. Okay, got it.
Present your entire screen, sir.
Your entire screen?
Yeah, yes, sir.
Can you see me now?
I can see you.
No, sir. You open your PPT, sir.
My PPT is here. This is the PPT.
But we are not.
But it is not visible, sir.
It's not visible?
Yeah, sir. You just again open your PPT, sir.
Yeah, I opened my PPT. That's what I'm telling you. I already opened my PPT.
You got to share, sir. Share the PPT.
Now come to present now screen, sir.
Yeah, that's what I did.
Click on present now, sir. Your entire screen.
Let me cancel this one. And let me present the entire screen.
Yeah, okay, sir.
But if I present, if I do, I can see your.
Then one window is open, sir.
Which one?
If you click on your present entire screen, means a small window is open, sir, in your screen.
Yeah, small window is there, yes.
Yeah, just click on the window and click share, sir.
Why I'm not getting this one? Okay. Can you see something?
Yeah, sir. Now we are seeing your presentation, sir.
Oh, okay, good.
Okay.
Presentation, okay, ma'am.
Sir, go to the full screen mode, sir.
Okay.
Go to view, full screen view, sir. Yeah, it's good, sir. Sir, now can you please speak with our head, sir? Principal?
Yes, sir.
Yeah.
Sure.
Ma'am?
Yes, hello, sir.
Hello, doctor. How are you?
Yeah, so nice of you to spend time for us.
Yeah, you know me and K. Karthikeyan. He is my collaborator since a long period of time, and he put the request. So how can I deny it? So that's why I accepted his request.
Yeah, I understand. So kind of you to be present for this international webinar on fractional system with the Rosenblatt process and Poisson jumps, optimal controllability, and the title is so so good and fashionable. Maybe so it's too technical for us. Maybe mathematicians might be very familiar with the technical term what you have used. But anyway,
Thank you so much. I'll be glad if you like this one. If you will like this one, I'll be glad.
Yeah. I understand. So I take this opportunity to welcome you for this international webinar arranged by the Department of Mathematics of KPR Institute of Engineering and Technology. And I welcome HOD Mathematics, Dr. Ramasamy, and Dr. Karthikeyan, and our guest speaker, Dr. Dimple Chalichehar. And it is, I think the time is up, and we'll start the program, and we are waiting for your enlightenment. Thank you.
Thank you so much.
Yeah.
So still 5 minutes. Yes, please.
Sir, HOD sir.
Yes, sir. Yeah, pleasant and progressive good evening to
Sir, give a formal speech, sir. Later we will record it, sir. Sir, just introduce, sir. சார் சும்மா விட்டு 4 வார்த்தை பேசுங்க சார், அப்புறம் வந்துக்கலாம் ரெக்கார்ட் பண்றதுக்கு. 5:50
Hello. Hello, Dr. HOD. How are you?
Things are going on, sir. Doing good, sir.
Nice.
I have done lot of work in Markov model, sir. I am a stochastic man.
Oh, that's good.
I have done in non-Markovian bulk arrival, general bulk service queuing systems with breakdowns, controllable services. And
okay. Oh, that's good.
I have collaborated with Professor Nagesh at Carmel University, USA, sir.
HOD sir, shall we start, sir? Sir, we shall start.
Yes. Yeah, pleasant and progressive good evening according to Indian Standard Time, and a productive good morning to the resource person according to Greenwich Mean Time, to everyone who has assembled here online through the multimedia platform using modern gadgets and willing to be participants in the one-day international webinar on fraction system with the Rosenblatt process and the Poisson optimal controllability. First of all, on behalf of the KPR Institute of Engineering Technology Management, Principal Dr. Magila, Chief Executive Dr. Natarajan, I feel honored and privileged in welcoming the resource person, Canon, Dimple Chalichehar, Professor of Mathematics, Director of Math Study Abroad Program, Member of BMR Liaison Committee, Department of Applied Mathematics, Virginia Military Institute, Lexington, Virginia, US, to this August online gathering. I warmly welcome you, Professor.
Thank you.
I am delighted in welcoming all the participants who are gathered here online from various parts of the globe. I sincerely welcome you all. Also, I wish to place on record my sincere and heartfelt thanks to our KPREG management, our beloved Principal Dr. Magila, Chief Executive Dr. Natarajan, for having permitted the Mathematics Department to have given the necessary means to proceed with the one-day webinar. The resource person, Canon Dimple Chalichehar, is holding various offices, namely Professor of Mathematics, Director of Math Study Abroad Program, Chair of International Program Committee, Member of Virginia Military Institute Research Laboratory, Liaison Committee at the Department of Applied Mathematics, Virginia Military Institute, Lexington, Virginia, US. And he has more than 54 research publications in peer-reviewed international journals, 60 plus presentations in the conferences, including invited talks with one monogram, editorial board of 11 journals, and reviewer of 25 plus journals. Reviewed 120 plus research articles for peer review journals, guided 6 3-year guide and 3-year co-guide students for PhD courses, 15 students for graduate and undergraduate level independent research. And also, he has published so many books, Calculus 3 with Hartman, Calculus 2 and Calculus 1. He has received so many awards, not to be cited, the 2020 Jackson Pope Prize for Excellence in Published Scholarly Work, BMI Institute Ceremony, BMI Grand Inay Summer Research Award, Jackson Pope BMI Matthew Fontaine Maury Prize for Excellence in Research Mathematics, BMI Institute Ceremony. And also, he is, as of now, he is working as Professor of Applied Mathematics at the Virginia Military Institute, BMIRL. The Rosenblatt process is important because it is one of the so-called Hermite process, which is a limit of normalized sums of long-range dependent random variables. The simplest Hermite process is the Gaussian fractional Brownian motion. The Rosenblatt process is the simplest non-Gaussian Hermite process. It has continuous non-differential path and is similar with stationary increments. It is Murray-Rosenblatt who first conceived of it. and this is why the name. A fractional system will be discussed with the Poisson jumps, optimal controllability by renowned resource person for the session. Now I request our principal madam to give a signal to the speaker to start today's session. Madam, please.
Sir, we had a casual talk before the session. So now that the HOD has mentioned all the credentials and accolades taken by you, we feel so great today to have you here for the presentation of the webinar. Sir, you can start, sir. Thank you.
Thank you, Dr. Principal. Thank you, HOD. Thank you, Dr. Karthikeyan, both K. Karthikeyan and S. Karthikeyan and the team. Thanks for the invite. Without wasting time, I just would like to start with the topic. And first 55 minutes, I'm going to talk about this article. And then after last 5 minutes, I just would like to spend for the question answer session. I hope all you guys can see me on the screen. Am I right?
Yes, we are able to see it.
Thank you so much. So let me start with this one. So my today's talk that is based on the optimal control for fractional stochastic integral differential system driven by the Rosenblatt process with Poisson jumps. So first of all, I'm just going to give you the introduction, and then after I will go for the preliminary. The main objective of this talk is so many people, big shots in control theory, I would say the stochastic control theory, they are in confusion right now, nowadays, I would say since last 6 months, because Rosenblatt process is very new as far as concern of stochastic control problems. And some big sorts, they think that fractional Brownian motion can be approximated by the Wiener-Ito process, Wiener-Ito integrals, but not the Rosenblatt process. So that's what I would just like to present over here. In my opinion, the Rosenblatt process can also be approximated by the Wiener-Ito integrals for m equal to 2, or you can say Wiener process. So that is the main objective of this talk. And then after I'm going to see that is included in the preliminary section. And then after I'm going to represent, I'm going to represent the existence and uniqueness of the problem. And after completing this existence and uniqueness of the system, then after I would like to start with the optimal control, how this optimal control is associated with the given stochastic problem. And finally, applications and the conclusion. So as I told you that first 55 minutes, I will just try to explain to you. And if you have some doubts, in that case, I will try my best to convince you. Thank you, guys. So let me start with this one. So first of all, introduction. So how this, you can see the title. It's a fractional stochastic integral differential system driven by the Rosenblatt process with the Poisson jumps. So I would like to introduce all of these terminologies, what we mean by the fractional stochastic integral differential system, what we mean by Rosenblatt process, and simultaneously the fractional Brownian motion, what we mean by Poisson jumps, what are the applications, and how we can apply all these terminologies to the optimal control problem. So that's what we are going to discuss initially, and then after I will start with the comparison. I mean to say the Rosenblatt process is approximated by the Wiener process. So let me start with this one. The fractional differential equation is about to generalization of the integer order and derivative of the arbitrary order. The potential applications of the fractional differential equations are in many fields of engineering and science fields, STEM fields, you can say, mainly for the fluid flow, electrical networks, and control theory. And lots of people are working since now, I would say last couple years or 3 years, people are diverted to this new system, to new branch of mathematics. And another thing I would just like to highlight, that is the Poisson jump, what we mean by the Poisson jump. For example, if a system jumps from a normal state to another state, the strength of the system is random. And that's why in order to make more realistic model, a jump term is included in any dynamical system. And the study of stochastic differential equation driven by the Poisson jumps has given the considerable attention since last few years. And these are some references. These guys are working in this field. I don't want to go through this one because you can also find the references at the end of this talk. And then after, I just would like to discuss about the fractional Brownian motion. So it is utilized, they are utilized largely due to its self-similarity, stationary of the increments, and the long-range dependence for the more models. And more details, you can refer some of the books. Tudor, he introduced this one, the Rosenblatt process, and that's why I would request all you guys to refer this book. It's a very nice book based on Rosenblatt process. All the details, the preliminaries, so many things, the properties of Rosenblatt process are given over here, and how Rosenblatt process that differs from other process, the other distributions. So that is given in this book. So I would prefer to refer this book. That's a nice book. And subsequently, Tudor with the Mejema, they established some new properties of the Rosenblatt distribution recently. And then after, just in 2017, these guys, San and Rand, they obtained the set of conditions for the existence of the solution of neutral stochastic partial differential equations with the Rosenblatt process, but without jump process, without Poisson jump in the Hilbert space setting. And then after, let me just go through this one. I'm sorry. What we mean by the optimal control. So optimal control is largely applied to medical science, mainly biomedicines, to model the cancer chemotherapy. And recently it is applied to epidemiological models and the medicine. And the main goal of optimal control is to find, in an open loop control, the optimal values of the control variables for the dynamical system, which maximize or minimize a given performance index. And when the fractional differential equation that describes the performance index, that means then the optimal control problem that is considered as the fractional optimal control problem. Fractional optimal control problem. And then after, I just would like to go through, why my cursor is not moving. Okay. Yeah. So using the fractional variational principle and the Lagrange multiplier technique, R.P. Agrawal, he discussed the general formulation and the solution scheme for the Riemann-Liouville fractional optimal control problems. And the subsequent work that was extended by H.R. Herat, and then after, you know that these guys, they have investigated the solvability of the optimal control problems for the fractional stochastic differential equation. So motivated by this aforementioned research work, in this work, we derived the sufficient condition for the existence of the solution of the following class of optimal control problem for the fractional stochastic integral differential system, which is driven by the Rosenblatt process with Poisson jump. And my system that is like this. You can see here, this is the system. And let me just explain to you the system components. This C dt alpha, that is nothing but the caput of fractional derivative of order alpha. Alpha lies between 0 and 1. That's why it's a fractional order. State xt, that is in the Banach space X, so X value stochastic process. Control U, that is control function U, takes the values from the separable reflexive Banach space U. A is the infinitesimal generator of the semigroup, or you can say the resolvent operator. So this A, that is from the domain of A, is contained in Banach space X to X, is the infinitesimal generator of a resolvent operator S alpha. B, that is the B of T, that is a family, of the linear operator from U to X. And this function F, that is from our interval 0 to tau to Banach space X to X. And sigma is nothing but 0 to tau to x2. This is L2 q to the power half y and x. Why I chosen this space, I will let you know this thing in the next 5 minutes. And this is nothing but my Rosenblatt process. This ZH that represents the Rosenblatt process. And my H that is from 0 to tau to x cross control space U to x, a nonlinear function, and x0, that is the script F0, that is a filtration measurable X value stochastic process independent of the Rosenblatt process ZH. So this one is the independent of this Rosenblatt process, and that is with the finite second moment. Let me continue with the space setting. So here omega script F, the filtration, and the null space, that is P, be a complete probability space furnished with the complete family of the right continuous increasing subsigma algebra, where script ft, t belongs to 0 to tau, satisfying that script ft that is in F. So ft denotes the sigma field generated by ZH. That is important. This filtration that is generated by the Rosenblatt process. and the P is a null set. And ZT is the Rosenblatt process with Hurst parameter H lying between half and 1, of course, open interval, on the real separable Hilbert space Y. The collection of the strongly measurable square integrable X value random variable that is given by this one. So now onwards, when I say that L2 omega X, it is to be understood that we are working with L2 omega script F and X, which is the Banach space equipped with this norm. And it is easy to prove that this one is a Banach space because you can choose any Cauchy sequence in this space and try to prove the convergence of that Cauchy sequence in the same space so that you can find the complete nonlinear space, which is a Banach space. And then after we can go for Lyx, that is the space of all bounded linear operators from Y into X. And if you take X equal to Y, in that case, we are going to denote that one by Ly. And Qy represents a non-negative self-adjoint operator. And we introduce some Y0 in my Hilbert space Y, you can say. So Y0 is Q to the power half Y, which is endowed with the inner product, this one. So UV at Y0, that is nothing but, because Y is defined like this, Q to the power Y, square root of Qy. So Q to the power half U, and here it is V, so here it is Q to the power V in the space Y, that's a Hilbert space. And this is L20, that is a subspace of that is L2 Y0 to X, be a space of Hilbert schematic operators from Y0 into X. So it's a Y0 into X, and that's why we can say that's a subspace of this L2. And that's why phi in L20 is called the Q Hilbert schematic operators with this norm. So norm of phi, that is with respect to this one, and that's why I associated this space, mainly I would say this space, in the space setting of my system. And then after, if you take the inner product over here in L20, that inner product is defined in this form. And if you have this function phi and psi, they are same. In that case, you can get norm of phi square in this for a trace of this one, so matrices. Let's see with the space of all continuous function from 0 to P to L2 omega X. There's a Banach space of a continuous function from this interval to L2 space, satisfying this estimation. So suprema of this estimation that is finite. And X2 be the closed subspace of this continuous function space, consisting of measurable sigma T adaptive X valued process. And for all X belongs to this continuous, all functions from this space. And that is equipped with this norm. I would like to take one more function Qt, T belongs to 0 to T, 0 to tau, is a Poisson point process. And taking its value in the measurable space, that's control space U and B of U, with a sigma finite intensity measure VDU. And the difference, I mean, this is the martingale measure and the Poisson continuous measure that is given by n tilde. So this n tilde, that's what we have defined in our sigma function, in our system with sigma function. And then after, I just would like to mention this filtration sigma script of Ft that is defined in this way. And this sigmation that is produced by Qt Poisson point, whatever we have just defined previously in the previous slide. Oops, I'm sorry. Previous slide. And you can see that means the Poisson point process and is augmented where n is the class of P-null set. And P2 space, which we are going to work, that is nothing but the interval cross U to X, the space of predictable mappings H running from this one, satisfying this condition. And of course, I'm going to work with the optimal pair. So I need to define this optimal pair. That is nothing but the expectation E and integration 0 to tau and L of this one. So define the admissible set UAD, the set of all VT lying in this space and 0 to tau cross omega to U, such that V is sigma T adaptive stochastic process with this estimation. And clearly, if that, and that is non-zero, not a null space, and that is contained in LP space, and there is a bounded, closed, and convex set. And denoted by the set of all admissible state control pairs. Why state control pair? Because this X, that is my state space, that means we are going, that comes from the state space. And we are going to take this X as a mild solution of the system corresponding to the given control U. So that's why I wrote it down over here. I mentioned here the state control pairs. And that is in AAD, where X is the mild solution and corresponding to the given control. The main objective, that is to find the optimal pair X0 and U0 in AAD such that it satisfies this one. That is absolutely small. That means X0 approaching to this one. So main objective of this work that is like this, what is the contribution or what we are going to discuss in next 45 minutes. That is, to the best of our knowledge, up to now, no work has been reported to derive the optimal controllability for the fractional stochastic integral differential system, or inclusion, you can say, driven by the Rosenblatt process and with the Poisson jump. And as I told you that usually preliminary section contains only the preliminary which we are using in our subsequent work. But here in preliminary, I have included this question, what we raised in the beginning of this talk, that Brownian process is approximated by the Wiener process. What can we say about the Rosenblatt? Is Rosenblatt process also approximated by the Wiener process? In my opinion, yes. Fractional stochastic integral differential system driven by Rosenblatt process with Poisson jump is formulated here. And then after, the fractional calculus theory is effectively used to get the existence and uniqueness of the solution. And then after, we have considered the optimal control problem using the same theory. And finally, example will be provided to justify the, to illustrate the theory. So let me start with this one. First of all, I just would like to discuss a little bit about the Wiener-Ito stochastic integral, because that is the main purpose. As I told you that I'm going to explain that why the Rosenblatt process is approximated by the Wiener-Ito process or Wiener-Ito integral, multiple integrals. So first of all, let's have a little idea about I know all you guys are expert of these subjects, but even though, let me explain to you about the Wiener-Ito stochastic integrals. So if I have some set, suppose BT, T belongs to R, some interval, actually I would have written over here B1T because only I used BT as an operator in my system. So just please make sure that this is not exactly same BT which we are talking in the system, they are different. So or you can consider this B1T. That's fine. So BT, T belongs to R, be a standard Brownian motion with B0 equal to 0. A Wiener-Ito stochastic integral of order M is given in this form. So IMF, that is integration Rm to one, suppose dash here, f of x1 to xm and dbx1, dbx2 up to dbxm, where this f is nothing but the non-random kernel, and this dbx1 or dbx1 to dbxm, this dbx can be interpreted as a Gaussian noise mean 0 and the variance dx. And therefore, the expected value of this dbx or dbx1, dbx2, that is 0 if x1 is not equal to x2. And the expected value of dbx squared, that is equal to dx. And this prime, whatever the prime I have over here on the integral sign, upper integral sign, this prime indicates that one does not integrate over the diagonals. You cannot integrate over the diagonals of the matrix. So that is, one always supposes that x1 is not equal to x2 is not equal to xm in general. Then this ensures that expected value of dbx1, dbx2, dbxm, that is equal to 0. And that's why IMF has mean 0. So this is mean 0 that is more important. Then after, I would like to consider this IMF, that is a distribution in terms of this one. So this F, SYM represents the symmetrized version of my operator F, and this D stands for the distribution. It could be any distribution, maybe martingale, maybe joint distribution, it could be any distribution. And then after, the last integral that is now defined in the form of norm of x square, all f is lying in L to Rm, such that integration Rm norm of fx1 to xm square and dx1 dxm, that is finite for all f, as I told you. And we can write the same thing to define the integral, yes. So to define the integral precisely, one can first define it for the simple functions, and then one takes the limit in L to Rm. So that is the process. And while ensuring that thing, we have the isometry as expected value of this one square, that is equal to m factorial this one. And if you take this m equal to 2, I2 of f square 2 factorial, that is a distribution of I to f and is determined by its cumulants. And if f is symmetric, in that case, we have this estimation, and that was proved in the reference 27, that is the Tudor's. So Tudor has proved this one. I'm going to explain to you, I'm going to say, show you all the references later on, but this is the paper of Tudor. He explained this thing in his paper. I took this one from his paper, thanks to him. And for information about the multiple integrals and including formulas for the moments and cumulants. And integral 3 can also be represented in the form of the Parseval's formula, and that is given in this form IMF. This is just kind of definition, you can say, a distribution that is f tilde lambda 1 to lambda m and db tilde lambda 1 to db tilde lambda m, where this f tilde lambda 1 to lambda m, that is nothing but the Fourier transform of f, all functions f in L to Rm, and db tilde, all lambdas, lambda 1 to lambda m, all these terms that is viewed as the complex Fourier transform of dbx. And since this dbx is real, that means I can write db tilde lambda equal to db tilde negative of lambda. And that's why this integral 6, in this integral 6 is double prime. You can see over here, now I've changed my prime. Previously it was just single, now it is double prime. So double prime on this one, that means that one excludes the integrations on lambda 1 equal to plus or minus lambda 2 equal to plus or minus lambda m. And this made precise, this one that was done. Why this statement is true? Because this was proved in the, again, the reference of 28. I think that is a TACU. So TACU has proved this thing recently, I think so. Oh, yeah, you can see over here, these are the references that MA, Diop, that is this one. So whenever I say about these references, TACU 27, TACU 28, so there's a central limit theorem for the quadratic forms in the random variables having long range dependence, that is published in this one. Another work of TACU is over here. And 29 is Tudor, the analysis of the Rosenblatt process. Fantastic book. And another one is the Albin, the extreme theory of the self-similar process. So we are going to see this one. And let me just go back. Let me just go back to this one. So that is all about the Rosenblatt process. As I told you, equation numbers 3 and 6. Let me just go for the complete view. Just view and full screen so that you guys can see on the full screen. Okay. So the distribution between 3 and 6, whatever the equations I've explained over here, 3 and 6, is established as well as this formulation. Im f squared, that is in the form of this one. F tilde lambda norm of this one, and d lambda 1, d lambda 2, and that is finite. And now I just would like to represent a little bit about the fractional Brownian motion. To better understanding that the Rosenblatt process, which involves the double integration m equal to 2, in both those integrals 3 and 6, actually they are equivalent. That is best to describe first the representation of fractional Brownian motion, where we are taking m equal to 1. And fractional Brownian motion, that is BHT t greater than or equal to 0, is characterized by these three properties. The first one is for the fractional Brownian motion, Gaussian mean is 0. It has the stationary increment BH equal to 0. And self-similarity index h lying in 0 to 1, that is for any a greater than 0, bh of at and a to the power h bht have the same finite dimensional distribution. And for more detail, again, you can use the paper of TACU, because the whole thing that is explained over there in that paper. Now, these three characterization, those three parts, those three properties, that conditions are very much handy, because in order to check that the given single winner etostochastic integral represents fractional Brownian motion, it is sufficient to verify that the three conditions mentioned above are satisfied. And self-similarity stationary implements improve that can be written in this form too. E bh square t equal to sigma square and bht1 bht2, that is equal to this one. And later on, I will let you know this thing, the same estimation we are going to get for the Rosenblatt process too. And that's the reason there is one way of telling that Rosenblatt process will be approximated by the Wiener process. Anyway, right now, let's focus over here for the fractional Brownian motion. And here, if you take the sigma square equal to 1, that means yk, there's a difference between bhk plus 1 and bhk, k greater than or equal to 0. And the rank is given in this form. So yk is Gaussian stationary long dependence for the used parameter h, lying between half and 1. And that is because the rank that is lying in this one. And this yk is called the fractional Gaussian motion. Why it is called fractional Gaussian motion? Again, refer this paper of TACU. Then after, let's talk a little bit about the stochastic representation of the Rosenblatt process. And at the end of this one, you will realize this thing, why this Rosenblatt process can be approximated by the Wiener process. So Rosenblatt process ZT, t greater than 0, is a self-similar with half is less than h is less than 1. and the mean has the stationary increment, and it has therefore the same second order properties as the fractional Brownian motion. So I can write the second order properties for ZT, because ZT represents the Rosenblatt process. So that's why I can take this one is equal to Z square T, and instead of fractional Brownian, I can take the Rosenblatt process over here with the same fractional Brownian estimation. And however, the non-Gaussian, it is non-Gaussian, is expected as a Wiener-Ito stochastic integral for order M. This Rosenblatt process the following is very useful, and this satisfies this means following representation are useful. First one is a time representation, second one is a spectral representation, and a time interval representation of the Rosenblatt process. So this property will allow us to refer that Rosenblatt process can be approximated by the Wiener or Wiener-Ito integral of order 2, M equal to 2. The equations in the previous section hold, whatever equations I gave to you that hold in the sense of finite dimensional distribution. And that's why we don't use whenever we start. So some people, they are working with the optimal control. Some people, they say the controllability. Some people, they say it exact, but we don't use the exact controllability over here, because ultimately Rosenblatt process, we are working over here with the finite dimension, and that's why we just use the controllability result. Anyway, so in some of the papers, you may find this type of title. So please make sure about this thing. So estimation of ZT1 minus ZT2 squared, that is given by T1 minus T2 to the power 2h, where this 2h is greater than 1. That is always greater than 1. That means in other way around, we can say h is greater than half. And the Kolmogorov's criteria given by this guy that satisfies this is not differentiable in the mean square. So please keep in mind this thing, this Rosenblatt process that is non-differentiable is non-differentiable in the mean square. And even though we are looking for the approximation by the Wiener-Ito integral. So that is important. That is interesting too. Next is, yeah, so it is not differentiable. So let me write in this form that limit t tends to 0. Thanks to reference 7, he proved this one, that you can write it down, the Rosenblatt process by this limit. So limit t tends to 0, this square is equal to this one, and that is infinity. And in fact, it is almost surely non-differentiable. The argument is based on the self-similarity and is identical to the one of the fractional Brownian motion. Again, Tudor, he has mentioned this thing in his book. So for the Rosenblatt process is self-similar index with the used parameter lying between half and 1 and has a non-stationary and has a stationary increment zk plus 1 minus zk, that is delta zk. Let me denote like this one. And the long range dependent that is given by summation of expected value of delta z0 and delta zk, that is this one. And in fact, they have the exact same covariance, and the increment of FBM that is given in this form. So you can see over here, the increment of FBM, fractional Brownian motion, and that is now represented in the form of the Rosenblatt process, this difference or long range dependence of the Rosenblatt process, and that's right hand side is exactly same as this one. And as k tends to infinity. We presented several representations of the Rosenblatt process. While representations are very physical, they do not provide immediate information about the distribution. And however, since the Rosenblatt process is represented as a double Wiener-Ito integrals for m equal to 2. And one can use the general result due to Mazur, reference 31, on the probability of bounded for double integrals. And there is a universal constant c greater than 0, which provides us the probability of z1 greater than u, that is less than or equal to this c and this estimation, where sigma square that is equal to expected value of z1 square. And this guy, Albin, he proved.
Sir, sorry, we are not getting the presentation, sir. Please, Dimple, sir.
Hello, can you see me?
We are not getting the presentation, sir.
Oh, you are not getting the presentation?
Yeah.
No, sir, it is visible, sir.
Is it feasible or it is visible or not?
Visible, sir, visible.
Visible, right?
Yes, sir.
May I continue?
Karthikeyan, are you getting the presentation? Karthikeyan?
Sir, we are getting the presentation, sir. You
Okay,
can
sir,
continue.
Go ahead.
Okay, so you don't mind, right? Let me continue. Am I right? Because I can see over here, I share my screen and presentation is there. It is, I think you guys are able to see this screen. That's what my computer says. Yeah. Is it okay, guys? May I continue?
Yes, sir, please.
Yes, sir.
Okay, fine. So, yeah. So Albin, he proved this result. It's a fantastic result. He said that the probability of the supremum of ZT greater than U, and if you take the limit supremum of this probability of supremum of ZT greater than U and probability of Z1 greater than U with the product of U to the power 1 minus H divided by H, that is finite. Most important result, and this result actually allows us to say or to claim that the Rosenblatt process can be approximated by the Wiener process for multiple integrals m equal to 2. Here you can see that this U to the power 1 minus H divided by H that tends to infinity as U tends to infinity. And you can see over here also this 1 minus H divided by only this exponent. This exponent decreases from 1 to 0. Decreases. This is 1 to 0 as your Hust parameter increases from half to 1. So it's inversely proportional, you can say, the half to 1, and the greater similarity between the P probability of supremum of ZT and probability of Z1 greater than U for large values of U. So it's a fantastic result, and the martingale distribution of ZT has a probability density function, and this follows from the general result on the multiple integrals. And as remarked previously, the Rosenblatt process can be now viewed as the heuristically as the integration or integral of the derivative. And now integral of its derivative. Rosenblatt process is not differentiable, but now you can write using the heuristic parameter, you can say that that is the integral of its derivative. And however, again, Tudor, that one can use this point of view to show that the Rosenblatt process can be approximated by the sequence of semi-martingale. Now, one thing is sure due to Tudor that now it is possible to represent your Rosenblatt process as a sequence of semi-martingales. And indeed, and now we have to, so one thing is sure, Rosenblatt process can be approximated by the sequence of semi-martingales. But that is not enough. We are looking for the Rosenblatt process to be approximated by the Wiener integral. So how we can correlate these semi-martingales with our Wiener integral? That is not that difficult. It's quite easy. Look at over here. So if we define Z epsilon t by replacing this KH0U0, whatever in your in the reference 31, by this one we have this estimation, and we can express this integral in the form of this one using this reference. They have proved this result, so that's why I just exclude the proof over here. And we then observe that this Z sigma t is the integral over 0 to t, or we can say 0 to t, or you can write 0 to tau if you want to make a similar integral, a similar interval. It is 0 to tau of an adaptive process, and hence Z epsilon t is a semi-martingale. So this Rosenblatt process is now semi-martingale, and estimation of this Rosenblatt process, Z epsilon t, sequence of these semi-martingales minus ZT square tends to 0 as epsilon tends to 0. And one obtains that Rosenblatt process now can be approximated. This is the proof why the Rosenblatt process is approximated by the semi-martingales. And because this Z epsilon t is well defined as the integral of its derivative, and semi-martingales are in fact processed with the bounded variation, and the Wiener-Ito multiple integral of order k that is given in this form. And that's why you can see over here s minus yj. Let me write some x plus. This x plus is denoted by maximum of x0, and the constant chk is the normalizing constant that ensure estimation of zhk 1 square that is equal to 1. And we have this estimation, exactly same thing. This is the one-dimensional Rosenblatt process with the parameter, Hust parameter h lying between 1.5 and 1. ZH has the following integral representation because of this double integration, which comes from the Wiener-Ito integral, and that's why it is Rosenblatt process can be approximated by the Wiener-Ito integrals with m equal to 2. And this guy, that's why it is given that a sequence of semi-martingales can be represented in the form of the Wiener-Ito process with some particular ch equal to this one, and kh is given in this form, and ch that is given in this form. This is the beta function. All these things are given in Tudor's book. So finally, RHST, that is equal to this one. And now whatever the estimation we had for the fractional Brownian motion, that can also be approximated by the Rosenblatt process. So if you take one sequence like this ZQT like this, and Q is the non-negative self-adjoint trace class operator, then the above sequence, above series that converges in the space Y. This series is converging in the space Y. So once this series is convergence in the space, Hilbert space Y, you can say, then the Rosenblatt process is approximated by the Wiener process, because this proof that says us that now semi-martingales can be viewed in the form of the Wiener integrals. And that's why, that is the reason that why I said that, because I submitted this article previously just before a couple months to Journal of Optimization Theory and Application, and the referee, I know that guy, big shot in the field of control theory, he raised this question, that how can you take the Rosenblatt process, which is approximated by the Wiener process? He was not agreed with me, and that's why I just went through all this theoretical portion. And I'm thankful to Ram Kumar, he is my co-author for this paper. So thanks to him too. And let me continue. So now let's go for some other conditions. So now whatever I wanted to let you know, that Rosenblatt process can also be approximated by the Wiener process or Wiener integral of order 2. We require some other estimations to go for the existence and uniqueness of the problem. So if phi lying between 0 to tau to L to 0 satisfies this condition, integration of norm of this one is finite, then the above sum can be defined as x valued random. So expected value of norm of integration that is less than or equal to constant, and integral of the norm. So norm of the integral that is equal to integral of the norm. If you are working with simple dynamical system, at that time usually we are using, the Lebesgue dominated convergence theorem to prove the existence and uniqueness of the problem. But because we are working with a stochastic problem, you cannot work with that one. So that's why we have to rely on this reference, this estimation, and this one is proved in the reference 15. Then after, let me go for the another definition, the Riemann-Liouville fractional integral operators of order alpha, that is given in this form. All function f from 0 to infinity to r, there's a Riemann-Liouville function that is very well-known definition. All you guys know this thing. This represents the gamma function. And then after, let me go for the Kapudov fractional derivative. Last year, I went to Bulgaria at the same time. Second week of June, I was in Bulgaria for the international conference. They invited me. And I met one lady, again, the big shot of control theories. And we had a good discussion based on the Riemann-Liouville problem and the Kapudov derivative. Yeah, I don't want to include that part over here, but please try to make sure about these two things, because Riemann, some people, they said that you cannot work with the Riemann-Liouville problem, but you have to work with the Kapudov fractional derivative. But she claimed that, no, you have to work with the Riemann-Liouville problem. But again, that is another topic of discussion. It takes at least half an hour to explain that thing. So let me skip that part over here. But if somebody is interested, he or she can go through that part too. Anyway, so if f is an abstract function with the values in x, then the integrals appearing in this definition, previous definition 2.1 and 2, that is the integral that is in the sense of Bochner. And the two-parameter function Mittag-Leffler type is defined in the series like this, in this series. And C is the contour starts and end at negative infinity and encircles with a disk. So norm of lambda is less than or equal to this one. And that is in the anti-clockwise or counterclockwise, you can say. And my resolvent operator that is generated by A, we are using over here the sectorial of, we are just using one sector of operator forms, and that's why it is called the sectorial operator. This is the definition of sectorial operator. And this resolvent operator that is generated by the infinitesimal generator A, and that is bounded by this one, m tilde, where m tilde is positive constant, divided by this one, this is non-zero. And furthermore, in the same book, the same paper, reference 24, they have defined this thing. A linear closed densely defined operator A belongs to A alpha, if and only if lambda to the power alpha belongs to this one and lambda belongs to this one. And this norm is bounded by this one. We are using all these things in our existence and uniqueness problem. So let me first start with very simple problem. Cauchy problem, you can see on your screen that c to the power alpha dt alpha xt, I just consider over here axt plus ft and x0 equal to x0 initial condition. And the simple Cauchy problem, the mild solution of this simple Cauchy problem that is given in this form, xt equal to s alpha t and t alpha. This s alpha is nothing but the mild solution, or I would say, yeah, it's a semigroup, kind of semigroup generated by A, and t alpha, that is the resolvent. For this property, this function, this s alpha t and t alpha t, that is defined in this form. Again, Tudor. So you can see over here, this T alpha that is called the resolvent family, alpha resolvent family, S alpha, as I told you, there is a solution operator. I would like to define one more operator, d to the power alpha u or nu, that is given in this form, and d alpha is this one. And whatever my solution operator S alpha that is bounded by MS, and my resolvent family T alpha that is also bounded by this one. And then after we can go for the mild solution of the system. The mild solution of the system that is given by this one. So, and in the filtration, adopted stochastic process xt from the space of all continuous function from the interval to L2 space is called a mild solution of the system 1 if for any control, for each control u in LP is measurable and the following stochastic integral is satisfied. So xt equal to s alpha t x0 plus integration 0 to t alpha t minus s. I'm going to divide because I want to prove the existence and uniqueness. So first of all, I just want to go for the boundedness of this xt, and that's why I just want to divide this right-hand side, this mild solution, into 5 different integrals, 5 different parts. This is my first part. I would like to denote by simply gamma 1, just a symbol. Here gamma is not the gamma function, just a symbol. So gamma 1, then t alpha t minus s ds us, that is my gamma 2, t alpha t minus s with this second part, that is my gamma 3 nonlinear function. This is sigma function, that is my gamma 4, and this is gamma 5. This is my gamma 5. So then we can do like this. Now we are doing existence and uniqueness. So we can go like this. Before I start this existence and uniqueness, I require some of the assumptions that my f is Lipschitz continuous with, and that is bounded also. It satisfies the growth condition. Sigma is Lipschitz continuous, like it's satisfying the low growth condition. H is little bit weaker condition, L1 Lipschitz continuity, and you can see over here that is also bounded by, that is, and the growth condition is satisfied. Operator B that lies in L infinity, and that stands for the norm of the operator B in the Banach space L infinity. And multi-valued map, that is the 0 to tau 2 to the power u phi, has closed, convex, and bounded values. And this operator, there's a graph measurable contained in phi, and phi is a bounded subset of u. So if this h1, h2, and h3 are satisfied, if these 3 conditions are satisfied, then after we can go for the existence and uniqueness of the problem for any control u in UAD for some p alpha greater than or p such that p alpha greater than 1. So as I told you that, let me just define my mild solution. Let me attach my mild solution with some operator form. So let's define the operator g from x2 to x2 such that gxt equal to this one. And as I told you that we are looking for the mild solution, we saw that this is the mild solution of the system 1 in the given interval, it is enough to show that this operator g has a fixed point in the space x2. So fixed point in the space x2, that means first we are going to see that gx2 is contained in x2. So if I take any x in x2, and then after I can go for this expected value of gx square is less than or equal to some constant, and this one, where gamma 1, as I told you, just a representation, it's not a gamma function, representation of my first term, gamma 2 my second term, third term, like this in a mild solution or the operator form, previous 14, equation number 14, operator form. So gamma 1 is naturally, by assumption, it is bounded. Gamma 2 I can use over here. You can see from here to here I have used Cauchy squares inequality, and I just proved the boundedness of gamma 2. I don't want to go through the complete proof because you guys are smart enough to do these things. So that's why let me just proceed quickly for the theoretical portion. Here again I have used the Cauchy squares inequality, and I have proved that gamma 3 is bounded, and same way gamma 4 is bounded using my first assumption H1. And then after gamma 5, same way that is also bounded, and that's why I have the expectation of GXT square that is bounded a kind of growth condition. Oops, sorry. Kind of growth condition. Where A and B, these are suitable positive constants. So G maps X2 into itself, and that means that is done. Now we are going to prove that this operator G has a contraction. So let me take two operators Gx and Gy, and let me use again my mild solution. The difference of these same terminologies. Integral, say norm of the integral that is equal to integral of less than or equal to integral of the norm. Let me use that property. And finally, I have this estimation. You can see here, I'm sorry. Yes. So finally, I have this estimation, and you can see this one is a constant. So if this constant is less than 1, that means we have contraction is nothing but the Lipschitz continuity with the Lipschitz constant less than 1. So that's why it's a contraction too. And it is not that difficult to prove that whatever the mild solution we have, that mild solution corresponding to our control U, that is bounded, expected value of this one that is bounded by some constant M. And proof is really very simple. Yeah, you can use the mild solution and all these things, whatever we have proved earlier, use that fact, all your gamma 1, gamma 2, gamma 3, gamma 4, and gamma 5. And finally, we have the mild solution, and that's why by using the Grunwald's inequality, the boundedness that is attained, and that is in X2. So boundedness in X2. So that's why we have the existence and uniqueness of the problem, and that is really very well known. And now I would like to start with the optimal controllability. So for optimal controllability, I require a little bit more assumptions. So one more assumption is, suppose we have a function L defined from the interval cross X cross U to R union infinity, such that the integrand L is filter measurable, script ft measurable. This integral is sequentially lower semi-continuous. And actually, we are using over here a vicar of, that function is measurable with respect to the first variable and continuous with respect to second and third variable. So it is indeed, it is convex on U for each x in X and almost all t in the interval. And this estimation for some d positive and e positive, d greater than or equal to 0 and e greater than 0, this estimation, this one is less than or equal to my integrand LTXU. And now I have this theorem. Suppose H1 to H4 hold, then the Lagrange problem 2 admits at least one optimal pair. Optimal pair, this X0, U0, this X0 is nothing but my state variable, my mild solution corresponding to my control U in AAD curve, such that this estimation, this is satisfied. So that's what we mean by the optimal control. Now, if I want to prove this optimal control, that means if my LXU, XU in AD, that is infinity, nothing to prove, but suppose it is finite, in that case, I am going to use my last assumption, new assumptions H4, particularly for the optimal control problem. That implies that, look at over here, I am going to consider my sequence of the state variable corresponding to my control terms, corresponding control terms, XM, UM, and I want to prove that this sequence is convergent. So if I am able to prove, if I minimize this sequence, that XM to UM tends to infinity as M tends to infinity. First of all, let me take care of my control portion. So suppose I have this sequence, because this sequence UM, suppose I am able to show that sequence UM is convergent, then it converges to U0, sequence XM converges to X0, and then after by Baldwin's theorem, thanks to Baldwin, he said that you can take the order pair, and this order pair that is also converges. So XM UM converges to X0, U0. So that is my aim for this particular portion. So first of all, let me start with UM. UM is contained in UAD for M equal to 1, 2, 3, and so on. And UM is a bounded subset of a separable reflexive Banach space LP. So there exists a subsequence. I denoted UM, but you can denote UMP or UPM, something like that, some subsequence. Subsequence, and that subsequence is weakly convergent convergent to U0 in the same space. And whenever the subsequence is weakly convergent to that space, that means the sequence is convergent. And that's why we can use that functional analysis terminology, and we say that sequence UM, control sequence UM, converges to U0 by Mazur lemma. Mazur had proved this thing. And what is left out? That I want to prove that XM converges to X0. So let XM be the sequence of solutions. My XM, that means my mild solution, I would like to write in terms of my sequence like this. So XM, that means here it is UM, XM, everywhere I have to make the corresponding changes. That is my XM. Simultaneously, I can write X0. And then after I will try to make, I will try to take the norm of XM to X0, and it is absolutely small so that XM converges to X0. That's what we are going to prove. So here is XMT defined in the form of this mild solution, and I'm going to define X0T in the form of the mild solution. And then after I take the estimation of XMT minus X0T. And that estimation is like this, that 4E norm of 0 to T alpha and this one. And if you use our assumptions, Cauchy-Schwarz inequality with my assumptions, last assumption H4, we have this estimation. So by applying Grunwald's inequality, finally, we ended up with this terminology, this expression. But you can see over here that BUM minus BU0, that is converges to 0, because B is strongly continuous. So that's why, because of the strong continuity of B and UM converges to U0, already we proved it. So that's why BUM minus BU0 that converges to 0 strongly, of course, in LP space, whereas M tends to infinity. And once this one is convergent, that means this is absolutely small. So expected value of XMT minus X0T, that is also convergent. Or other way around, I would say that XMT converges to X0T as M tends to infinity, as M tends to infinity. And that is the final one, is a sequentially lower semi-continuous order pair XU converges to this one, is a sequentially lower semi-continuous in the strong topology of L1, 0 to tau 2x, and the weak topology in LP contained in L1. You know this LP spaces. And hence this order pair X0, U0 is weakly lower continuous, semi-continuous in LP. And because of that last assumption, my order pair that is greater than or equal to this one, and it attains this estimation, sigma equal to this one, and that is greater than this one. So we have this estimation. And finally, based on this one, I would claim that we have proved the optimal controllability of the given problem. And finally, I just would like to go for the applications. I know I don't have much time. Only I have 5 minutes now. So let me finish this example in 5 minutes. And then after, we will conclude our talk. So this is the example, not difficult. Caputo derivative fractional order 2 by 3, because alpha lies between 0 and 1, is delta, and my BTUT that is given in this form. Instead of F, I just mentioned over here F tilde. So F tilde is given in this form, and this is my sigma function with the rust parameter of Rosenblatt process. And here you can see my H function over here. Whenever you work with this type of problem or any problem, you know this thing, even if it's dynamical system, and when you apply your example, try to match your example with your system. At that time, you have to make sure about the domain of the function, and you have to work a little bit for that one. Mostly you are taking help of Sobolev space over here to fix your domain. So here Z belongs to domain of A, and A is equal to this one. My UAD, that is collection of all those functions U, controls U, I would say. Sorry. Control U. All those controls U such that norm is less than or equal to 1. And whatever the terminologies, I said that I would like to compare this one with my system, my main system 1. So my XTZ, that is this one, initial condition, BUTZ, that is defined in this form, my operator F, that is defined in this form, operator sigma, that is in this form, and H operator with this N null space, that is in this form. And this problem can be written as the abstract formulation of a system 1 with the cost function, this one. This is my cost function. And this is my LTXTUT. And this LTXTUT that is written in the form of integration of omega 1 XTZ square and omega 1 UTZ square. So it's again a combination of my state variable, or I would say mild solution corresponding to my control U, like this. And it is easy to verify assumptions H1 to H4. And hence, there exists, we can say, the optimal control pair x0, u0 lying in L0 space such that my cost function jx0, u0 is less than or equal to this cost function for all xu belongs to L2 space. So I think all the conditions are satisfied, and that's why we can say that the given system in this example that is optimal, that satisfies, or that is the optimal control problem. And finally, let me go through the conclusions of what we did in this talk and what is the future prospects of this work. Though, let me go through this one. In this paper, you can, or in this work, I would say that we studied the existence of the solution and the optimal control results of fractional stochastic integral differential system driven by the Rosenblatt process with Poisson jump in Hilbert space. The sufficient condition for the existence of mild solution results are formulated and proved by virtue of the fractional calculus solution operator and the stochastic process, or you guess stochastic analysis techniques. And then after, we have proved the existence and the uniqueness of the problem, existence of the optimal control of the proposed problem that is presented using the Baldur's theorem, and the optimal control analysis for the fractional stochastic differential inclusion with distributed delays, time-varying delays, state-independent or state-dependent infinite delay, impulsive effect. This will be a future work. Yeah, you can include over here the delay portion. That delay could be time delay, it could be state dependent delay, it could be finite delay, it could be infinite delay, like this. And yeah, somebody can go for the numerical estimation of the same problem too. First, the problem, whatever we have considered over here, and then after the problem with the delay. So please keep in mind this thing. And whenever you are working with the delay portion at that time, I would request you, please refer my paper that was published before few years, Jota paper, Journal of Optimization Theory and Application. In that paper, I clearly mentioned that if you are working with infinite delay term, at that time, you cannot work only with the phase space. You have to define some particular phase space for your delay part. So if it is finite delay, you can work with the phase space, which people are usually using, Hall and Kato phase space. But if you are working with the infinite delay, please make sure that you cannot work with the Hall and Kato phase space. You need to define some other phase space, and that is given in the book of Hino Murakami and Naito. And that is the new phase space, new definition that was given in that paper of Jota 2012. In my paper is there. So you can find that one and try to extend the same problem using the infinite delay stochastic optimal control problem. So I think, yeah, let me conclude my talk. And these are the references I have used over here to prepare this lecture. And you can go over this one. Already I gave you main references which I used over here. As I told you, let me remind you again that there is nothing but mainly this one, that 21, 22, 23, 24, not this one, but actually, yeah, Balder fixed point theorem is given over here in 25. Main references are over here, 27, 8, 9, 30, 31. So these are the main references, because most of them, they are the books, and very nice book based on the Rosenblatt process. So I think, yeah, my time is already up. I have taken 1 more minute. I'm sorry about this. And thank you so much for patience hearing. And I really appreciate. Thanks for the invite. And thank you all.
Professor, some of the participants have raised their doubts, Professor. Could you address the answers for the doubts, Professor? In the chat box, they mentioned the doubts, Professor.
Yeah, I can't see anything over here. Yeah, or somebody can ask me, or you can do one thing. You have my email. Just send that. If you have some doubt, you can send it to my email and I will get back to you. I will try my best to convince you. But I can't hear any one of you guys. If you have some problem, you can write it down so that I can speak here.
Okay, Professor.
Professor, whether the control theory and the Ito calculus are related, Professor?
Use your chat box.
Professor?
Yes?
Whether control theory and Ito calculus are related, Professor?
Control theory and what? I can't hear you.
Control theory and Ito calculus.
Control theory and what?
Whether control theory and the Ito calculus are related, Professor?
They are related, yes, they are related. But make sure that whenever you talk about the control theory and Ito process usually we are using for the stochastic problem. Whenever it is not a continuous process, at that time we are using this one. Of course, they are related.
Whether Rosenblatt process is coming under Poisson process or what, sir? Whether it is obeyed Poisson.
I'm not getting you. I can't hear you, my friend. Who is there?
Whether Rosenblatt process is Poisson process or not process.
Hello? I'm sorry, I can't hear you, man. Is there any way you can write it down over here, or I can see you? May I close this window so that probably I can see you guys?
Professor, we will mail all the questions to your mail, Professor.
Yes, now I think I can see you. Yeah, please go ahead.
Okay, Professor.
Okay. Yes. So may I ask Dr. Sumitra to give vote of thanks, madam?
Thank you, sir. Warm greetings to all. Joy is the simplest form of gratitude. Let me to thank Dr. K. Karthikeyan and Mr. S. Karthikeyan for giving me the joy of delivering vote of thanks. Let me to take this wonderful opportunity to thank our eminent speaker, Professor Dimple Chalsager, Virginia Military Institute Lexicon, for accepting our invitation, irrespective of his busy schedule. Thank you very much for your informative presentation, sir. Nextly, I would like to thank all the participants, those who have responded for our invitation. Nextly, I would like to mention a special note of thanks to Mr. Rajkumar, Assistant Professor of Civil Engineering Department, and his team for supporting us in live streaming of this program. Finally, we would like to thank our management, principal and chief executive for their continuous support and encouragement to organize this kind of program. Thank you all. Be safe and stay healthy. Thank you, sir.
Thank you so much, and same to you. Thank you so much. Thank you, Principal. Thank you, HOD, and all your team. Thank you, Dr. Karthikeyan.
Thank you, sir. Thank you, sir.
Sorry, a few words from the Karthikeyan, sir. Few words.
Few words for Karthikeyan?
Yes.
Yeah, he's a nice guy. And as I told you in the beginning that he started collaborating with me since, I'm going to say in 2011, 2012. And then after we have published almost 10 papers, almost I would say, maybe 10 plus. I have not counted. And he's a nice guy and hard worker too. Yeah, so whenever I send him some work, and you won't believe, but just within 3-4 days, he got back to me. So nice guy. Probably you will be happy to have him in your institution. He recently joined your institution, right? Yeah. And I'm glad that your HOD is also working in the same field. So maybe in future we will have some collaboration.
Okay, sir.
Thank you, sir. Thank you, sir.
Thank you so much. My pleasure.
Thank you very much, sir, for the good words about Dr. Karthikeyan. Thank you, sir.
My pleasure. Thank you. It is out. Okay, guys. Thank you.
Thank you. Dear Professor, thank you very much for the wonderful support given by you for this international webinar. For the past 6 years, we are jointly published 12 papers in reputed journals. Our research was also focusing in this topic. Once again, I thank you, Professor, for the acceptance by invitation and gave the wonderful lecture. For the past 55 minutes, I thank our principal, Dr. M. Akila Madam, HOD, Dr. K.S. Ramasamy sir, CFRD head, Dr. M. T. Sumitra Madam, Civil Department Rajkumar sir, Manikandan sir, for their wonderful support to telecast this lecture in YouTube. Nearly 2,000 people are watching this live session. Thank you, sir. Thank you, sir.
2,000? Wow, big audience. Good. Thank you, guys. Thank you so much. Yeah, any one of you have or your audience have some question, just send email to me, and I will try my best to get back to you soon. Thank you, guys. Thank you.
Thank you.
Bye. Please send the link to me, please.
Yeah, definitely, sir. We will send the link to you, sir. Link to your mail ID. Okay.
Thank you.
Thank you.
I appreciate it. Thank you. Yeah.
ஹெச்ஓடி சார்.
சார் கார்த்தி இருக்கீங்களா?
சார் இருக்கிறேன். ஓகேங்களா?
கங்க்ராச்சுலேஷன்ஸ் கார்த்தி, டூ கார்த்தி.
சார் ஓகேவா?
சூப்பர் சூப்பர் சூப்பர்.
சுமித்ரா மேடம் பேசுவோமா?
எக்ஸலென்ட். Are you able to hear my work?
மேடம், சுமித்ரா மேடம்.
சுமித்ரா மேடம் போயாச்சு.
சுமித்ரா மேடம்.
கார்த்தி நான் பேசுறது கேக்குதா கார்த்தி?
கேக்குதுங்க சார். சார் நல்ல விட்டு கேக்குது.
சுமித்ரா மேடம் லெஃப்ட் வெளிய போயிட்டாங்க மேடம்.
சுமித்ரா மேடம் இருக்காங்க சார் லைன்ல.
இல்ல இது இல்லையா? அது கேக்குதா? மேடம் உள்ளதா இருக்கு.
மேடம்
உள்ளதா இருக்கு.
சார் ஹெச்ஓடி சார் எப்படி இருந்தீங்க சார்? எப்படி
நல்லா பண்ணாங்க.
थैंक यू சார்.
ஒரு 10 கேள்வி எழுதி வந்து கேட்கலாம் பார்த்தா முடியாது.
சார் நீங்க மெயில் கொடுங்க நாம வாங்கிடலாம் சார் ஆன்சர். டைம் ஆயிடுச்சுங்கறாருங்க சார்.
இது இப்படி ஃபாரினர்ஸ்லாம் அந்த டைம் கரெக்ட்டா செய்வாங்க போல இல்லையா?
ஆமாங்க சார். ஆமாங்க சார். அங்க இன்ஸ்டிடியூஷன் அப்படிதாங்க சார்.
சரி சரி. சூப்பரா இருக்கு. நல்லா இருக்கு.
ஓகே थैंक यू சார். थैंक यू.
மணிகண்டன்
சார். மணிகண்டன் சார்.
சார்
மணிகண்டன் சார் வெரி थैंक यू சார். ராஜ்குமார் சார் வெரி थैंक यू.
ராஜ்குமார் இருக்காரா?
ராஜ்குமார் போயிட்டாரு சார். மணிகண்டன் சார் இருக்காருங்க சார்.
மணிகண்டன்
சார்.
மணிகண்டன் thank you பா. thank you very much.
Thank you sir. Thank you.
For your technical support.
Sure sir. Yeah. So duty sir.
பரவாயில்லை. சார் அப்புறம் வேற சொல்லுங்க. யாரா இருக்காங்க?
ராஜா இருக்காங்க சார். ராஜா
சார் யார் வீட்டுல உட்கார்ந்துருக்கீங்க? வீட்டுல உட்கார்ந்துருக்கீங்களா? இங்க யார் வீட்டுல உட்கார்ந்துருக்கீங்க?
சார் எங்க வீட்டுல உட்கார்ந்துருக்கீங்க சார்.
ரெக்கார்டிங் இருக்கு. ரெக்கார்ட் பண்ணிட்டு இருக்காங்க. கட் பண்ணி இருக்கு. ரெக்கார்டிங் பண்ணிட்டு.
ஓகேங்க சார். ஓகேங்க சார்.
செல்வி சார் ரெக்கார்டிங் போட்டுங்க. ரெக்கார்டிங் கட் பண்ணி.
ஆமா சார் ரெக்கார்ட் பண்ணிக்கிறேன் சார்.
ரெக்கார்ட் கட் பண்ணி போதும். ஆனா இப்ப கட் பண்ண ரெக்கார்ட்.
அது ஒண்ணு இன்னி யூடியூப்ல போகாது ராஜா. யூடியூப்ல கட் பண்ணியாச்சு அவ்வளவுதான்.
ஓகே.